Hello everyone. In this lecture, I am going to introduce a new way of solving linear systems that is called iterative methods. So, in the past couple of lectures, I have introduced the direct methods. Those includes Gaussian elimination with partial pivoting, and then LU decomposition. Today, iterative methods are quite beneficial in terms of numerical computation when you are going to solve linear system of equations. In direct method, for example, in Gaussian elimination, we need to do order of n cube operations for solving a n by n linear system. So, it will be something order of n cube. However, the method which I am going to introduce today, Jacobi and Gauss Seidel, we need to do only order of n square operations in each iteration. So, if number of iterations are less, that is less than n, then these methods are quite beneficial when compared to the direct method. So, however, these techniques can only be applied to square linear system. Square linear systems means you are having a number of equations together with a number of unknown variables. So, basically iterative methods for Ax equals to b begin with an approximation to the solution x naught that we use to say initial solution. Then we seek to provide a series of improved approximations x1, x2, etc. that converge to the exact solution. In engineering problems, this approach is appealing because it can be stopped as soon as the approximation xi have converged to an acceptable precision. Means whenever the difference between the exact solution and the solution in any iteration is less than a given threshold. The iterative methods are good to use for the problems where the matrix A is large and sparse. Okay. And in these cases, if the matrix A is large and sparse, they are much faster than the direct methods. So, let me introduce these methods in a general setting. So, if we are having a system Ax equals to b, where A is the coefficient matrix, x is the vector of unknown variables and b is the right hand side vector, then an iterative method for solving this linear system can be written as in this form, where P is called the iteration matrix, Q is a column vector, and for any x obtained in kth iteration, we can get the update on x in k plus 1 iteration as xk plus 1. Now, how to write this P and Q? That is the difference in various methods, those coming under the category of iterative methods. As I told you, we start with an initial solution x naught. So, P x naught plus Q will give us x1, then in the second iteration x2 will be P x1 plus Q and so on. So, in each iteration we update our solution and we with an assumption that solution is going to converge to the exact solution. However, it is not true always. Solution may diverge also for a given iterative scheme. Now, how to write this particular matrix P, that is the iteration matrix, and the column vector Q. So, as we know, we can always write a given n by n matrix A as the sum of 3 matrices L plus D plus U into X equals to B, where L is a lower triangular matrix, D is a diagonal matrix and U is an upper triangular matrix. For example, if you are having a 3 by 3 system given by the coefficient matrix A as this one, then I can write this coefficient matrix A equals to a lower diagonal matrix plus a diagonal matrix plus an upper triangular matrix which is given as A11, A12, A13, 0. Here A11 will not come as I have taken A11 already in diagonal matrix, in that is capital D. So, this is the matrix capital L, this is the matrix capital D and this is the matrix capital U. Now, we are having different scheme under the category of iterative methods. First of all, I want to introduce the most simple scheme, that is called Jacobi method. In Jacobi method, what we used to do? We used to write this system as dx equals to minus L plus U x plus b. So, what we have done? We have taken these two terms into right hand side. Now, what I will do? My iterative scheme will work like this, that at k plus 1 iteration x is given as from the estimate of x in kth iteration, or I can write xk plus 1 equals to just multiplying both sides, pre-multiplying by d inverse. So, it will become minus d inverse L plus U xk plus d inverse into b. Here, if I compare this particular scheme with a general formula of iterative scheme, that is given by xk plus 1 equals to p times xk plus q. So, the iteration matrix P is given by this particular matrix. The right hand side, the column vector q is given by this term. It will be a n by n matrix and this will be a n by 1 column vector. So, this particular scheme is called Jacobi iterative scheme. Here we will start with an initial solution x naught, then I will find x1 using this formula and so on. In a more simple setting, if I want to write the iterative equations for this particular scheme, I need to consider a system of 3 equations with 3 unknown. Let us say the coefficient matrix A is given by this one and vector x is x1, x2, x3, and right hand side vector b is b1, b2, b3. Okay. So, now this is the linear system x equals to b. The first equation can be written like x1 k plus 1 equals to 1 upon a11 into b1 minus a1 to x2 at k iteration minus a13 x3 at k iteration. So, what I have done? I have taken the variable which is corresponding to diagonal element of the coefficient matrix in the left hand side, and I have taken the rest of the 2 terms of the coefficient matrix in the right hand side. Similarly, from the second equation we can get the iterative equation for the variable x2, and it is given as 1 upon a22 b2 minus a21 x1k minus a23 x3k. Finally, from the third equation I can write the iterative scheme for x3. So, x3 k plus 1 equals to 1 upon a33 b3 minus a31 x1k minus a32 x2k. So, these 3 iterative equations can be updated simultaneously to get the iterative values of x in each iteration. Now, I will take an example and I will solve it using this Jacobi iterative scheme. So, here let us take this system of equations. Here I am having 3 equations with 3 unknowns x1, x2, x3. The iterative equations can be written in this way: x1 k plus 1 will be 1 upon 4 at minus 2 x2 k minus 3 x3 k, x2 k plus 1 equals to minus 1 upon 5 into minus 14 minus 3 x1 k minus 2 x3 k. And similarly, from the third equation I can write the iterative equation for x3, that is x3 k plus 1 equals to 1 upon 8 into 27 plus 2 x1 k minus 3 x2 k. Now, if I start with an initial solution, let us say x1 0 is 0, x2 0 is 0, x3 0 is 0, then in the iteration 1 I will get the value of x1 1 as 2, that is coming from the first equation. Here I am putting x2 0 is 0, x3 0 is 0. So, x1 1 will become 8 upon 4. So, it is coming out as 2. Similarly, from the second equation I am getting x2 1, that is coming out to be 2.8, and x3 1 equals to 3.375. Now, if I put these values in the right hand side of these three iterative equations, I can get the next iterate of x, and that will be, for x1 it will be minus 1.931, for x2 it will be 5.350, and for x3 it will be 2.825. If we need a solution correct up to 3 places after decimal, then we need to calculate this sequence of values for further k. So, using the same, this table gives me the values of x1, x2, x3 in third iteration, then in fourth iteration, and you can see the values are changing quite differently in each iteration. Going in the same manner, in 22nd iteration it is coming out minus 1.025, for x2 it is 2.976, for x3 it is 1.973, and then in the next iteration the values can be seen like this. After 43rd equation, that is in 44th iteration, I am getting the value x1 as minus 1.001, x2 as 3 and x3 as 2. In 45th iteration I am getting minus 1, 3 and 2. Then in 46th iteration I am getting minus 1, 3, 2. So, in 2 successive iterations I am getting the same value, hence my solution converges to minus 1, 3 and 2, and which is the exact solution also of the given linear system. So, here we have taken 46 iteration to solve this 3 by 3 system using the Jacobi method, and this is the this example gives an illustration of the Jacobi method. Now, as I told you, we have taken 46 iterations to solve a 3 by 3 system just by starting with an initial solution 0 0 0. Hence, I can comment on the convergence of Jacobi method, and I can say it is having a slow convergence. So, in the next method, that is called Gauss Seidel method, I will introduce some modification in the Gauss Jacobi scheme, and then Gauss Seidel method iterative equations will give a bit faster convergence compared to the Jacobi scheme. If we see the iterative equation of this Jacobi method, here you can see in the second equation I am using the value of x1 from the previous iteration. However, before going to the second equation, I have find out the value of x1 in the current iteration. So, here the value of x1 from the current iteration is available to me, but I am using the old value. Similarly, if you see the third equation, here both the values of x1 and x2 are available to us from the current iteration, that is at the k plus 1 iteration from the first two equations, but what we are doing, we are still using the values which we obtained in the previous iteration. If I modify these values from the values of current iteration, then I can have a bit more faster convergence. For example, like in the first equation I will calculate x1 at k plus 1 iteration, and what I will do here, I will use this value. From the first and second equations, I will get the value of x1 and x2 respectively in k plus 1 iteration, and in the third equation I will use these new values. So, basically in a general setting, what I am doing, I am having a system x equals to b, again I am writing it L plus D plus U x equals to b, and then what I am doing, I am writing this D plus L x equals to minus ux plus b, and from here I am writing my iterative scheme, that is D plus L at k plus 1 iteration equals to minus u x k plus b. So, this equation can be written in a more appropriate form like this, just I am pre-multiplying by the inverse of this matrix. So, it will become minus D plus L inverse u x k plus D plus L inverse b. So, this particular equation gives the Gauss Seidel scheme in a general setting, where my coefficient matrix A is n by n matrix. Here iteration matrix P can be written as minus D plus L inverse into U, and the column vector Q is given as D plus L inverse into B. If I compare this scheme with the abstract equation of an iterative scheme. So, this scheme is called Gauss Seidel method for solving the linear system of equations, and if I use this method on a 3 by 3 general system A11 x1 plus A12 x2 plus A13 x3 equals to B1, and other two equations like we have taken in Jacobi method, the final system comes out to this particular 3 iterative equations. The only change is, as I told you earlier also, here we are using the updated value of x1 and x2 in second and third iterative equations respectively for finding the values in the current iteration, that is k plus 1 iteration. Hence, we hope that this scheme will be more faster because we are using the more updated values of the variables in the scheme. Let us take an example of this method. So, the same example which we have taken in the earlier case, that is in case of Jacobi method, there we use or we need to use 46 iterations for finding the exact solution, means for the convergence of the solution. Here let us see how many iterations we need using the Gauss Seidel method. So, for that particular example, the 3 iterative equations, that is for x1, x2 and x3 can be written in this way. So, here you can note down this particular term and these two terms, here we are using the updated values as I have told you in the derivation of this particular method. Then if I start with an initial solution, that is x1 0 equals to x2 0 equals to x3 0 equals to 0. So, initially I am taking a 0 vector as the initial solution, then in the first iteration I am getting the value. So, here I need to put x2 equals to 0 and x3 equals to 0. So, what will happen once I will put the 0 0, I will get x1 1 as 8 upon 4, that will be 2. Now, in the second equation I will not use here x1 equals to 0, because if I will use here x1 equals to 0, that will be something that will be exactly like Jacobi. Here I am using this updated value of x1, that is 2. So, this will become x21 equals to minus 1 upon 5 minus 14 minus 3 into 2, that is minus 6 minus 2 into 0. So, here x21 will become minus 20 upon minus 5, that is 4, and so x21 will become 4, and finally x31 will become 1 upon 8 27 plus 2 into 2. Please note that here again I am using the updated value of x1. In Jacobi method I have used here 0, that is the value from the previous iteration. So, 2 into 2 4 minus 3 into 4 12. So, 27 plus 4 minus 12. So, it will be 27 minus 8, so 19 by 8, and that will be coming out something like 2.375. Now, in the next iteration I will get the value x2 in the second iteration, x1 is minus 1.781, x2 equals to 2.681 and x3 equals to 1.924. Then these are the values in the third iteration. Then we are having value in fourth iteration and so on. Continuing this calculation, in ninth iteration I am getting the value x1 is minus 1, x2 is 3, x3 is 2. In the 10th iteration I am getting x1 is minus 1, x2 is 3 and x3 is 2. So, hence my iterative scheme converges in 10 iteration itself, while in case of Jacobi method it was taking 45 iterations, but here in Gauss Seidel method it converges in 10 iterations. Hence, the claim which we made that by using these two updates Gauss Seidel method will be something more faster than the Jacobi method is verified by this example. Now, in this particular lecture we discuss the two iterative schemes for solving linear system of equations, and we have seen that the latter one is quite faster than the earlier one. Hence, an iterative scheme is good if it is more faster. So, the effort should be made in the for developing an iterative scheme by taking care of its convergence or rate of convergence, how fast it converges to the exact solution. In the next lecture I will talk about it, and then I will introduce one more technique to you, that is basically called successive over relaxation. In this particular technique I will use a relaxation parameter. I will find out the optimal value of that relaxation parameter, and then based on that optimal value in terms of convergence speed. Once I will get the optimal value, I will get my iterative system, and using that particular iterative system, I will write the iterative equations. Further, in the next lecture, I will also introduce about the conditions for convergence of an iterative scheme. So, thank you very much for this lecture.